So let's start. So before doing the physical design or using this tool, we'll have some lectures, like some review of the previous concepts, which we will need in this class actually. So I will just review some concepts. So you already know that like the main goal of this program is to like give you some idea about microelectronics, like that we have done so far. We have learned different basic concepts, starting from the very basic theorems and then semiconductors, all those MOSFETs, right? And another goal was like to design a chip, right? Hopefully. So for designing a chip, we need to design this layout. So we call that CMOS layout or physical design. They are the like exchangeable terms. So in this class, we will learn how to design this layout and how to create this physical design for different circuits. So as I mentioned before that, we will review some concepts because MOSFET or transistor is the basic building block of CMOS technology, right? We use PMOS and NMOS because they have the complementary or the opposite behavior. So we use them to design different circuits. And with that, we can design any chip, any CMOS chip or any electronic chip, right? So, and this is the structure of MOSFET. I think you have seen that before. You have learned the basics of these things. So we will give you a very high level overview in today's class about this device. So in MOSFET, we have uh, how many terminals are there in a MOSFET? Do you remember? Do you remember MOSFET? So we had gate, source, drain, and we had body, right? So you had 4 terminals in a MOSFET. So can any of you tell me which type of MOSFET is there, and like how many MOSFETs are there? Like how many types of MOSFETs we have? Two. What are them? PMOS and NMOS, right? PMOS and NMOS. So how, like, can any of you tell me is this the structure that is shown in this slide? Is this NMOS or PMOS? PMOS, and any other answers, or everyone agrees with him? P-type substrate, yeah, P-type substrate. And so is this PMOS or NMOS? Just okay. So the answer is NMOS. It's NMOS because you'll have to look at the source and drain, the yellow like yellow portions of the device. You can see that like those are the source and drain. So you can see these are N plus. That means these are N-type dot, N-type material. So if the source and drain are N types, it's NMOS. Substrate will be the opposite one, PMOS, P-type. And in P, if you have a PMOS, then the source and drain will be P plus, P-type material, and then substrate will be the opposite one, N-type material. Okay, so that's the way you can like know which type of MOSFET is this. Is it NMOS or is it PMOS? Okay, so I'm repeating again. So it will need that. So the source and drain, if those are N type or N plus, they are NMOS. And if the source and drain are P plus or P type, then it's PMOS. And substrate will always be the opposite. For NMOS, the substrate will be P type, and for PMOS, the substrate will be N type. Like the substrate is always opposite. Okay. And substrate is also known as the body, the fourth terminal that we have. And the gate is here is typically metal or a polysilicon. We'll learn about that later. So this is again another review of N type and P type, just to understand. Like in NMOS, we have N type source and drain. In PMOS, we have P type source and drain. So do you remember what is N type and what is P type? Do you remember that? So we like the advantage of using semiconductor in electronics is that we can use other materials like which are not semiconductors. We can mix them or add them in the semiconductors, and we can control the behaviors or the properties of semiconductor. Right? That was one of the major advantages. And we talked about this. We had two different types of semiconductor: intrinsic or pure, where we don't have any other material. We only have silicons, or we only have semiconductors. So these are pure semiconductors, right? Then when we add impurities, we call them impurities or other non-semiconductor materials, then we can have two different combinations. We can use either trivalent atoms, which have 3 electrons in the outer shell, or pentavalent atoms, which have 5 electrons in the outer shell, right? And then we can have two types of materials system, which we call p type or n type. We remember, I think p type means the positive type. You remember, like there will be more number of holes. Do you remember the holes? Holes is the absence of electron. So electrons are negatively charged, and if we have any absence of electrons, that means we don't have any negative. That means we are positive, the opposite thing. So that's why p type, positive type. So when we add trivalent atoms like boron, which have 3 electrons in the outer shell, if we add them in this silicon material, with this silicon material, in silicon or in any semiconductors, we have 4 electrons in the outer shell, right? They are tetravalent. Remember that, right? Silicon has 4 electrons, but when you add boron, they have 3 electrons, right? So these 3 electrons will combine with 3 of the electrons of silicon. So we will have one empty hand, you can say, one free hand. So that means we have one absence of electron. And any absence of electron is defined as hole. So if we add one boron or one trivalent atom, that will create one hole, right? So now if we add more and more boron or trivalent atoms, that will create more and more holes. So in p-type materials, we will have more number of holes and less number of electrons. That's why in p-type, the majority carrier, we call them majority carrier is holes and minority carrier is electrons. And similarly in n-type, we'll have the opposite thing. We'll have 5 electrons in the pentavalent. So 4 of them will combine with 4 electrons of the silicon, right? So we'll have one extra electron. We call them free electron. So if we add more and more pentavalent atoms, then we will have more number of electrons here, right? That's why in n-type, negative type, we have more number of electrons and less number of holes. Okay, so you don't have to remember all these things. You just have to remember, like in p-type, we have more number of holes or electrons. Holes. That's the main thing. In p-type, we have more number of holes. We call them majority carrier. We have less number of electrons. They are minority carrier. And in n-type, we have the opposite thing. In n-type, more number of electrons. Majority carrier is electrons and less number of holes. So minority carrier is holes. Okay, you just have to remember this. And again, you have seen this before. I think this is the 2 types of MOSFET we discussed, NMOS and PMOS, and these are the circuit symbols when we make design circuits. You did some circuit simulation in the circuit lab tool, right? So there you have seen some of these MOSFETs, like this symbol. So these are the symbols where, as I mentioned, you have 4 terminals: gate, drain, source, and body. And typically in NMOS and PMOS, body terminal is connected with the source. That's why you can see that in the last column here, this column, you can see the body is not there, right? We only have gate, drain, source. So that's the reason, because this body is actually connected to source in most of the time. You can say all the time. So if that's connected to this then we can like consider one terminal for both body and source. That's why we only see 3, right? Okay, so this is the most simplest, and when we design circuits, and in most of the textbooks, you will see these symbols mostly. Okay, so these are the circuit symbols, and again, this is the basic. I will give you a very high level overview how this NMOS and PMOS work. So I think you will remember that from your previous classes. So let's talk about only NMOS. So in NMOS, initially, this source and drain, current always flows from drain to source in NMOS, right? So if current flows from drain to source, what will be the direction of electron flow? What will be the direction of electron flow? Same as the current or opposite as the current? I think it was like discussed in the very first class. So we have a relation between electron flow and a current flow. So what's that? Like the same as the current flow or the opposite as the current flow? No, it's opposite. So if electron flows from A to B, this is A, this is B. If electron flows A to B, then current will always flow from B to A. Current and electron, because electron is negative and current direction is always positive. Like if current flows from B to A, we call them positive current, and electron is negative. So that's why the opposite relation. Okay. So here in NMOS, the current will always flow from drain to source. So this is the direction of current. So electron will flow from source to drain, the opposite direction. Okay, so initially you can see that this is n plus, this is n plus, and the blue region is p type. We talked about this, right? In NMOS, the substrate is p type, opposite thing. So there will be no electron flow because this p type is like has a lots of empty spaces, lots of holes. We discussed that. In n type we have electrons, right? In n type here we have electrons, but in p type we have lots of holes, positive charge. So this positive charge will actually not allow this electron to flow from source to drain. And for that, we'll have to apply a voltage to this gate. And when we apply this positive voltage to this gate, so what it will do, this positive voltage will repulse these positive charges. So we, as I mentioned, there are lots of positive charges in this p type. So this positive voltage will repulse this positive voltage from this surface, and a empty space will be created here between the source and drain. Then if we apply a voltage between this source and drain, then this electron can be like attracted from source to drain, and then we will have current flow. Okay. That's what we can see here in this. If you look at this curve here, you can see like up to 2 volt. You can see that up to 2 volt, the current is like ideally the current should be 0, but you can see there are a very small amount of. Okay, so that's what you can see. We call that off condition, right? Because there is no electron flow from source to drain and there is no current flow. So this is like a switch off condition. And if we apply high enough voltage, which can create an empty space, as I mentioned, between the source and drain, then we will have significant amount of electron flow and we will have significant amount of current flow. As you can see, current is increasing exponentially after that. So this is the on condition, you can say. This is on and this is off. Similar thing is there in the positive PMOS. So we'll discuss that later. So so you can say like the transistor is like a switch. So we all are familiar with switch, like, right? So if we turn off the switch, there is no current flow, right? That's why all the electronic appliances turn off because they don't get any current. But if we turn on the switch, then we have a large amount of current flow and we can turn on other like everything, right? So transistor is similar thing. So if we don't apply a high enough voltage, because we call that a threshold voltage. You can see this VT here. This is the threshold voltage. So if we apply a voltage less than the threshold voltage, it's like off. The transistor is off. And if we apply a voltage larger than this threshold voltage, then the transistor is on. Okay. So there are just like 2 states, you can say off and on. Okay. So it's like a switch. And for NMOS, as I mentioned, we will have to repulse these positive charges. So we'll have to apply positive voltage here. So 0 or for negative voltage, that device will remain off. Okay, so not sure. So for NMOS, if we apply 0 or any negative voltage, 0 or negative voltage, the NMOS will remain off, as I mentioned, because we'll have to, the main mechanism is that, let me. The main mechanism is that there are lots of positive charges here, holes. We'll have to remove these holes from this region, right? That's the main mechanism to create the current flow. So what are you doing here? The Mac guys, what are you doing? Why are you smiling? Sorry. Okay, so can you please look at these slides, right? That's why you are here. Okay, so and you can even like turn off the laptops now. You're not taking any notes, I guess. So yeah, so the main mechanism for creating current flow is that here we have a lots of positive charges holes. We'll have to remove them, and to remove positive charges, we'll have to apply positive voltage. That's why if we apply 0 or negative voltage, the transistor will remain off. And if we apply a positive voltage, enough positive volt, then it will turn on. Similarly, if we go to PMOS now, the substrate is N type. So here, what do we have? Holes or electrons in this region. This is N type. I have talked about this. Like in N type, we have a lots of electrons. In P type, we have lots of holes, and in N type, we have lots of electrons. So this is N type. PMOS, this is N type. So we have lots of electrons here, right? So, and again, the mechanism is same. to create current flow, we'll have to remove these electrons from here. So to remove the electrons, what type of voltages do you need? Positive or negative? Electrons are negative. So you want to repulse them or remove them. So we need again negative force, right? If we apply positive force, that will attract them. So they will keep them at that place. But if we apply negative voltage, they will repulse them. So they will remove them, right? So the opposite thing will happen. In PMOS, if we apply 0 or positive voltage, it will remain off because the electrons will not be removed. They will remain at the same place. But if we apply enough negative voltages here, they will turn on. That's what you can see here. In the x-axis, the voltages are negative, right? So the mechanism is exactly same, just opposite thing happens. Like here in NMOS, we have to remove the holes and create a flow of electrons. In PMOS, we'll have to remove the electrons and create a flow of holes. That's the only difference. Okay. So again, like just only the takeaway message from this slide is that NMOS and PMOS both are just like switch. They can either be off or on, right? So for NMOS, if we apply 0 or negative voltages, they will remain off. So we'll not have any current flow. And if we apply enough high voltage, positive voltage, then it will turn on and we'll have current flow, right? And the opposite thing will happen for PMOS. Is that right? So again, you don't have to like remember these curves or equations or all these things. You just have to remember this high level understanding, like off and on, and when it turns off and when it turns on. Okay, right? So just let me ask you again, like for NMOS, if we want to turn on the NMOS, what type of voltage we need to apply? Positive. And for 0 or negative, it will remain off. Just remember this. And for PMOS, it's again like the opposite. So for PMOS, to turn it on, we'll have to apply negative voltage. And for 0 or positive, it will remain off. Okay. Just remember this. We'll need this later. So as I explained, the NMOS and PMOS has exactly opposite behaviors, right? So as I like, we call them complementary behavior, and that's the fundamental property for this CMOS technology that we use actually. So everywhere we use CMOS technology, in laptops, in mobile, in like any electronic products, we have this CMOS, like NMOS and PMOS. Okay, so we use them in this complementary fashion, and for any CMOS circuits, this is the fundamental way to design circuits. So we have two networks actually. We have a pull-up network and a pull-down network. Okay, so in pull-up network, we will always have we'll always have PMOS. We might have one or more. But they will always be PMOS connected in different fashions, like series or parallel. And in pull-down network, we'll always have NMOS. Okay, and so this is the basic building block, and the fundamental, the simplest circuit in CMOS that we can design is the inverter, where we have one PMOS and one NMOS connected in series, right? I think you have also seen like other larger circuits, right? And NAND, NOR, all those things. And Mazhar might also cover a bigger circuit as well, like how to design that from any logic function using this PMOS and NMOS, right? I think so. We'll not go to that complex circuits today, but we'll like learn the basic steps or basic flow to design this physical design or layout for this CMOS circuits. And the flow or the process that we'll cover will remain same for how complex the circuit is. Okay, so process will remain same. So we'll learn the process today. Okay, so we will design the inverter first. So we'll talk about that a little more. So as I mentioned, in inverter, we have a PMOS transistor and an NMOS transistor connected in series, and their gate. So this is the gate of PMOS, this is the gate of NMOS. They are connected together, which is the input of an inverter, and this is the source of PMOS, this is the source of NMOS, and these are the drain of PMOS and drain and NMOS. So both the drains are connected together, and that's the output here. Okay, so that's the circuit here. So as I mentioned, like CMOS, again, we are only considering digital circuits so far. So in digital, we have only two types of inputs, right? You remember that logic 0 and logic 1, right? In digital, we cannot have other like in between values. We only have logic 0 or logic 1. And that's how the computer works, right? Logic 0 and logic 1. So for logic 0, the input is 0 voltage. And for logic 1, the input is VDD, the supply voltage or the highest voltage that we can use, right? I think you remember these things. So when we apply this 0 voltage, so we have, again, we have two combinations like logic 0, 1, logic 0 input and logic 1 input. So when we, this is the logic 0 input, you can say, when we apply this 0, that means 0 voltage. So we have just discussed for 0 voltage, the NMOS will remain off or on? Off. NMOS will remain off because to turn on the NMOS, we need to apply positive voltage, high positive voltage. So for 0 voltage, the NMOS will turn off. You can see that the switch is broken. So there is no current flow here, I equal 0. And here we have the 0 voltage, and this is the source, right? So source has a high voltage. So VDD is actually 5 volt here. Okay. So if we have 5 volt here, and if we have 0 voltage at the gate, so what's the voltage between the gate and source here? So gate has a 0 voltage, source has 5 volt. So what is the voltage between gate and source? Is it 5 volt or negative 5? Again, like this is the gate, which is 0 volt, and this is the source, which has 5 volt. Now we are trying to understand the voltage between gate and source. So when we try to understand, get the voltage between two nodes, so gate is first. So we'll always have this type of relation. Gate voltage minus source voltage. Okay, so here we'll have negative 5. But if we want to calculate the source to gate voltage, then we will have positive 5. Okay, so the node that comes first, that will be the first, and the second node that comes, that will be subtracted from the first. So that's the way we calculate the voltage difference. I think you know that. So this is the voltage difference between two nodes. So here for the PMOS, for 0 input, we will have negative voltage, and we have discussed that. So if in PMOS, if we have negative voltage at the between gate and source, that will remain off or on? On. For PMOS, negative voltage turn on. So that's what you can see. It turns on. It has a resistance. So the current will flow through this. And because this is off, no current will flow there through this direction. Right? So, and for the opposite thing, when we have logic 1, that means we have 5 volt applied here. So if we have 5 volt, that means NMOS has high positive voltage, right? So if NMOS has positive voltage, that will turn on. Here we have resistance for the on state, and the PMOS will have now positive voltage, right? Not positive. Here we have 5, here we have 5. So 5 minus 5, that means 0 volt. And for PMOS, we need negative volt. 0 voltage can turn it on, right? That's why you can see this is off. And the current now will flow through only this path. There is no current flow through this pull-up network here. Okay, so as you can see here, for logic 0, this path is active. So this output will actually be equal to VDD or close to VDD through this resistor, because current will flow through this path, right? So output will be 1. For logic 0 input, we are getting 1 output. And when we have logic 1 input, this path is active, right? And this is ground, which is 0 volt. So output will be connected to 0 volt. You can see that. So we have 0, logic 0 output. That means we have the opposite. When you apply 0 input, we get 1 output. When you apply 1 input, we get 0 output, right? That's what the inverter is. It inverts the input. It inverts 0 input to 1 output and 1 input to 0 output. Okay, right? Is there any question about that, or is that clear? Like, again, you don't need to remember all these details. You just have to remember the high level understanding to have some idea or understand what we are going to do in today's class. Okay, I think I'm again talking about this from very high level. I think these circuits have been covered in greater details in previous classes, I think, because so we are again just using these circuits in today's class. So as I mentioned, the primary goal of today's class is to give you some idea about the physical design flow, or the steps that we use to design layouts or create physical design of any circuit. Okay, and this is actually the chip design flow diagram for chip design, you can say. So we always start with the specifications. So specifications tell you what type of circuits that you want to design. For example, if someone tells you design an inverter, okay, so that's the specification. And you typically we know about inverter and we have just talked about that, right? So when someone tells you to design an inverter, you know what type of circuits you need. We will have to convert the input into an output so that they have inverting relation, right? For logic 0 input, you have logic 1 output. For logic 1 input, you have logic 0 output. So you all know, you know that this from this specification. Now, if someone tells you to design some other circuit instead of inverter, there again the input and output and how the circuit works will all be mentioned in this specification. Okay. Then the second step is this architecture design and logic design. So based on the specification that you are given, you will have to design this circuit. So here, since the specification is design an inverter, so you'll actually design something like this, right? So this is the inverter circuit. So you will design something like this. So this is the second step. And the third step is logic verification, right? So you'll have to, so the circuit that you design, you'll have to verify that first, if that is correct. So to do that, you'll have to do some simulation first. And you know, for inverter, we have for logic 0, we have logic 1 output. For logic 1, we have logic 0 output, right? We know that. And that's what we are seeing in the simulation. You can see that this is our input. So we have 0 input, we have 1 output, we have 1 input, and we have 0 output. So we have opposite behaviors like the inverter, right? So this simulation actually verifies the circuit design that it's correct. Okay, so if the simulation tells you the circuit design is not correct and it's not working properly, then what you'll have to do, you'll have to go back, you'll have to modify the circuit design, and you'll have to again do the simulation and verification until you get the perfect result or the proper result. You will have to do this iteration. You'll have to modify the circuit and you'll have to do the same step again and again. Okay, so after you verify that okay, the circuit is now working properly, then the next step is the physical design, as you see. So that's what we'll learn today. So after we design some circuit and we verify their functionality, we will go to this physical design step where we create the layout, and again here we'll also have to verify. So after we create the physical design or create the layout for the circuit, we'll have to again verify if this is working properly, and we'll have to compare with this simulation results. Okay, so and also the specification that was mentioned, like inverter, right? So if the layout again does not work properly, you'll have to again go back. You'll have to modify the layout or physical design and then again do the verification. So in every steps you have verification. Now, for example, now suppose that the layout that you have designed is working properly from the after the verification. Then the next step is this chip fabrication. So we submit the physical design or the layouts to foundries or other groups maybe who can fabricate this, right? So if you remember in the very first orientation class, Dr. Aziz showed you some video of TSMC, right? So how they start with lots of sands, they collect silicon from that, and then they do lots of process and lots of steps to fabricate any circuit, right? So that's what is done here in this process. After you submit the physical design or the layouts, they do their steps and they fabricate these circuits. And after this fabricate, they actually send you something like this. I think you have seen something like this when you took you to the Gina lab, right? To show the probe station. There you might have seen something like this round where we had our circuits. So you get something like this. This is the fabricated chip, and here you can see in different parts you might have different circuits, or the whole thing might be one thing. It depends on the circuit you submit. So if you have a very large circuit, so the whole thing will have the same one thing, one chip, and the pads, the top level you see, those are the contact pads. So those will be your inputs and outputs. And in the bottom layer, in the middle layer, will actually have your circuits fabricated, right? So again, when you get this chip back, then the next step is again verification. So we use that probe station that we showed you, right? So we use that probe station and we place these chips inside them. We apply the inputs. For example, if we have an inverter circuit, so we will apply a pulse like 0 and 1, logic 0 and logic 1. That will be our input. And we will measure the output if for logic 0 we are getting logic 1 or not. And for logic 1 input, if we are getting logic 0 or not. Right? So that's what we do. We apply inputs and we measure the outputs. And then again we compare with the design specification that was mentioned. Right? So for inverter, we know that like for logic 0, we have to get logic 1 out, right? So if we don't do that, that means the whole thing that we have done has not worked properly, or in somewhere there has been an error. Okay, so we'll have to do the whole process again. But if the chip works properly, if we get the output that we are supposed to get, then like that's the best news, right? The whole thing that you have done is correct, is working properly, and you can go to the next step, whatever it is. Okay, so you see for every step, like this is the design step, there we have one verification. This is the physical design step, layout step, there we also have verification. And this is the final step after the fabrication, there we also have verification. And in any step, if we don't get the proper result, we'll have to go back and we'll have to modify our design or anything like that, to solve that error that we are getting, or solve the issue that why we are not getting the correct out, right? So we'll have to do that. And that's the iterative process. You can see that in the flow diagram. Okay, so as I mentioned, you actually have done up to this point, right? You have designed this inverter NAND gate in the circuit lab. You have done the simulation, right? You have verified their functionality there as well. So we will do that again today, because we will need those results to verify our physical design, right, or layout. So and then we will start the next step, the main focus of today's class. So I'll not do that. You will do the simulations, all those things that you have done again. This will be your review, you can say. And at any step, if you have any issues, I can help you, right? So and also in the slides we have the steps one after another. So I'll go through that, and you will actually do that. So the first step is to go to the circuitlab.com. Okay, so everyone, and like whenever you everyone does this step, then we'll go to the next step. So please do that. I'm not sure. I think they should have been shared. I'm not sure which class it was covered, so I'm not sure if the slides are there. So we have here everything. So you can just follow this. Yeah. No, we will do the inverter and NAND. So do you have that already? They don't on there, but I don't know where to go. But I think it will be better to like do it from scratch, right? So it will be again a revision for you. So I think you have gone to the circuitlab.com, right? Then the next step is login. If you have, I think you have created your account, right? Earlier. So just log into that account. Because without login, you will not be able to simulate some of the circuits. So it's better to log in to your account. I will check the output from everyone actually. So you'll have to do that. And if you can do it, like if any of you face any issue, just let me know in the beginning. Otherwise, at the end, if you tell me that like there's the issue, that will be difficult. Okay. So has everyone opened the circuit lab and logged in to their account? Okay. Yeah, then you can use that as well. So I thought that like, because I've seen that like if you don't have any account, that like stops you doing some circuits. Yes, yes. So I think yeah, you can skip this as well. So just go to the circuit lab and then click on new circuit box. Okay, just to open a new canvas like this. So open the new circuit box. Are are, are you all here? Just come on the new circuit. Go to file. New. Could you do it incognito mode? Yeah. Then you can. I'm not sure actually. So I actually have an account. This is a free account. So yeah. So you just click on the file, and like after you have this screen here that is shown here. After you have this screen, just click on file and then click on new. So that will create something like this, an empty canvas. Okay. So I think you have joined later, right? You. So like no the yeah. So have you been able to get here? Oh, I'm sorry. Sorry. Yeah. Okay, sorry. So yeah, if everyone is here in this empty canvas, then we can go to the next step. So are we all here? Like Mac guys, are you here? So it works on Mac, so there is no issue. So after if we are here, then we'll have to build this circuit, right? So we'll have to build this inverter here. We'll have to bring one PMOS. So first is to select the PMOS. So if you go here, you will see something like this, right? So in the component list, if you scroll down, you will see this MOSFETs, right? MOSFETs, and the arrow that is directing inwards, that's PMOS. So this is the PMOS, the first one, and the second one is NMOS. Okay, so you'll have to bring one PMOS and one NMOS and place like this. PMOS will be on the top. PMOS will be on the top, pull up network. NMOS will be on the bottom, pull down network. So NMOS is always at the bottom layer, and PMOS will always on the upper layer. So the top one is here PMOS, and the bottom one is here is the NMOS. So after you place the PMOS and NMOS, just then you'll have to use these essentials. You'll have to click this wire. You can see it here. Sorry, this wire, the third one. You'll have to click the wire, and you have to connect this drain, like drain of PMOS with the drain of NMOS, which will be our output. So you'll have to create something like this, and then you'll also have to connect the gate terminals of the PMOS and NMOS. Then you'll have to create like this, something like this input. So this is our input and output, and then you'll have to create an wire like this and like this. We'll do the VDD and ground later. So just connect the drain terminals, this portion here, connect the drain terminal and like make something out like as the output, and then connect the gate terminals like this and create this input terminal. Are flipped. No, this is NMOS and this is PMOS. The arrow that directs outwards, that's NMOS. It's actually taken from mother slide, so I've not checked this, so I'm not sure about that. Like, but So I think you have done this before, right? It's from one of his previous classes. Yeah, yeah, we know, but I've not done that in circuit lab as well. So yeah, but I think this is taken exactly from Mazar's slides. So he showed you these steps, and I think yeah, PMOS will always have to be on the top because that will be connected to the VDD, and NMOS will always be in the bottom. So follow the circuit lab. Follow like the N channel, put the N channel, MOSFET N channel, put that in the bottom, and MOSFET P channel, put that in the top. Okay. So after putting these two MOSFETs, MOSFET P channel, again, MOSFET P channel on top and MOSFET N channel in the bottom. Okay. After that, make these connections using these wires, connect the drains and create this output, and connect the gates, create this input. So are we done? Make the connections, making the connections, everyone? How about you guys? Yeah. Okay. So if you have done this input and output connections like gate and drain, then we'll go here. We'll bring in voltage source, which will be this VDD here, and we'll also bring in ground here, so which will be connected to the source. Okay. So I think it's not shown here. So here, so bring in VDD voltage source from there. So this is the DC source actually. So you will bring a DC source and we'll connect that with the source of the PMOS here. So this will be our DC source. Okay. Right. I'm like, this is mute. This is unmute. Yeah, yeah, I've checked that from mobiles. Yeah, yeah, sure, sure. Yeah. Did you bring the voltage source, the DC source? Yeah, bring the DC source and connect that with the source of the PMOS. And then also you'll need a ground to connect with the voltage source. And you'll also need to connect a ground with the source of the terminal. So make this circuit that you see here. Okay. So the ground is in the essentials, and the voltage source that you need in the DC sources palette. Okay. So from DC sources, you will bring this voltage source, connect that with the source of the PMOS, and bring the ground from the essentials, connect that with the source terminal of the NMOS, and also uh, on the negative terminal of the DC source that you apply. So have we done up to this point, everyone? Okay. So the next step is to apply the input, right? So we know that for for an inverter, we'll have to apply an input, and we showed something like this, like 0, 1, 0, 1, a pulse, voltage pulse. Okay. So to apply that, we will use this voltage signal generator from voltage signal sources. You can see it here. We bring that and connect that with the input terminal that we made by connecting the gate of NMOS and PMOS. Okay. So first do this step here. So bring this voltage signal generator and then double click on it on the voltage source. Then you'll see something like this. There you just put these values. Are we done up to this? Yeah, okay. We have applied the input and you have put in these values here, right? From the table. Yeah, then we have to just do one more thing, which is we applied a voltage. This is voltage source, right? From the DC source option, just double click on it and change the value to 5 volt. Yeah, I think it was uh, initially 1 volt. So change this to 5 volt, and then you will have something like this, this circuit that's shown here. Okay. Yeah, and then we will do the simulation. Sorry, 40 minutes already done. Yeah, that's why I mentioned, like, creating a free account is always better. Like, you can have unlimited time. Yeah. So are we done up to this point, right? Creating the circuit, and then we'll do the simulation. For that, in the left button, we have the simulate option. You can see it here. Click on the simulate, and then you will see something like this. And we will click on the time domain option. So click on simulate, then click on time domain here, and then you'll see something like this. Just put in these values here and run, and click on the run time domain simulation. And you should see something like this. So just to verify. Yeah, there. So yeah, I think. This out. Just click on that and you will see this. Okay, so I think there are again some mistakes in the slide. I'm sorry for that. So you'll have to go back to this stage where you make this circuit. So just click on the input. Sorry. Just double click on the input voltage, the V2 source that you have here. Okay. So double click on that and make the amplitude 5 volt, and the DC offset, make that 0 volt. Okay. Make the DC offset 0 volt and make the amplitude 5 volt. Frequency is 1000 hertz. It's okay. And then when you go here, like after simulate and click on the time domain, before run time domain simulation, you have to click on the input and output terminal in the circuit. So you'll have this circuit. So if you click on this wire here, just click, then you will see some like V of some node, something like that here after the outputs. And then if you click on the output, you will see another expression in the outputs. So you'll have two expressions. And then if you run the time domain simulation, then they will show the input and output voltages together. So these steps are missing from here. So sorry for that. Now is that working? You can change the input. So do you have like do any of you have why is not working? Yeah, you have. Sorry. I actually didn't check that fast. Yeah, another correction actually. So, so this should be like the DC offset should be 2.5 instead of minus 2.5. So it should be positive 2.5 and amplitude should be 2.5. Like both of these should be plus 2.5. So yeah, you just
Change it back to.
no, and make both of them 2.5, positive 2.5. That's how the signal generation defines. Now,
Keep that part.
yes.
It's looked at the other ones.
Should be
Oh, I have to switch.
yeah, I'm not sure. So,
Okay.
so now we'll have to
Okay.
see the yellow one is the input. This one is 1,000 and it's 0.
Okay. Thank you.
Okay, so have we got the output? Like, did you the output set down? Just make the DC offset and amplitude both positive one. You also understand that, right? When you want now this is the exact opposite.
Wait, is the monster influence?
Yes, yes. Okay, so you just click on the input. Click on the you want to see this, right? Then we 2.5 and amplitude also true. Now, we go to simulate. Yes. Now again, I think this positive. So just forget that slide. So that's not for reveal and so on the top we should have PMOS. So say yes. Okay, so connect the PMOS on the top of the software and the P channel. The P channel on top, the N channel on top. Yes, let's start. P channel on top, N channel and that.
Yeah.
Just yeah. Just put those values there and then click on the input and output in the circuit. Click on the input and output. The input comes. These are the two voltage you have to see. Things out. Put one slide. The yellow one is so you see that this is the zero, right? Zero ground is zero. When the input is not output should be 1 point 1. So you see. And when the input is logic 1, output is 0. Output is the opposite. Just click on that. So it works for all the time. Zero is the input, 0, 1, output is 1, input is 1, output is 0. Have you been flat? You got the output. So it's not and you have followed the slide. Yes. Yeah, and there are some messages. So it is like you see, this is the engine.
Yeah.
So but on top we always have Qs.
Yeah.
So these will be channel. So on top you have the Qs. Okay. And the P channel and then graph. Just change the and the P channel on top. P channel is the CMOS. CMOS on top and NMOS. Just the output depends on that. So if this is the output will go to So yellow one is the input. So this is logic segmentation. You are having higher logic one. So the input is logic one. So I think almost all of them have done the simulation, right? So I think almost all of us are here, right? We have got this result, right? So there, like the yellow one is the input here, and the blue one is the output here. So when the input is logic 0, we are having logic 1 as the output. When the input is 1, we are having logic 0 as the output. So exactly opposite behavior, which is the inverter. Okay, so from this we can say that the circuit is verified, right? So we have done up to this point. Now we'll go to the next thing, which is the physical design. Okay, so for that, again, I'll first give you some like overview of the physical design, then we'll do that like hands-on using the tools. Okay, so what is layout? So again, if you can focus on the slide again, that will be better. So the what is layout? Layout is, we know that like from the meaning, layout is nothing but a physical drawing. Okay, so physical drawing where we will tell that how the different components, like in inverter, let's just remember the inverter example in your head. So in inverter, we have two transistors, like one PMOS and one NMOS, right? So in the layout, we'll tell where the PMOS and the NMOS will be placed. Okay, so we know that like PMOS will be on the top and NMOS will be on the bottom. So in the layout, we'll tell that the exact placement, exact positioning, and also we know that like in the PMOS, inside the PMOS, we have different materials, right? For gate, we'll have to use one material. We mentioned that polysilicon. For the source and drain, we'll have to use N plus, right? For the NMOS, and for the PMOS, we'll have to use P plus, right? In the very first slide, we showed that. For NMOS transistor, we have N plus source and drain. For PMOS transistor, we have P plus source and drain, right? So we'll have different materials. Again, for NMOS, the substrate will be P type, the opposite. And for PMOS, the substrate will be N type. So we have different materials, and we'll also have to tell that which layer has which materials and which will go where. So it's like a physical drawing, you see. So the positioning will be there, the placement will be there, and also we'll have to mention the like the width, the dimensions, the length, the width, the area of different layers that I mentioned. Like for N plus, how wide will be that? Will that be? How long will that be? What will be the area of that layer? So that will be, and these informations we will need for all the material, all the layers there, right? So this is another information. And we have another information, which is the separation. So when we place this, like maybe one PMOS and NMOS, so they cannot overlap, right? So we'll have to keep them separated. So what will be the minimum separation between two components, between two layers? So we'll also have to tell them that during the layout. Okay. So layout is nothing but a physical drawing where we will provide all these informations, and we can make different circuits. We can connect the PMOS and NMOS as like the way we did in the simulation, right? We use wires, but in layout we have different ways to connect them. We'll talk about that later. So main components of layout is like we have two major components. I have already talked about one, which is the layers, right? So for different materials, we'll have to use different layers. So if we want N plus or P plus, we'll have to use the N plus P plus layers. If we want N type or P type substrate, for that we have dedicated layer. For making the connection, we need metal layers. So we have different layers that we'll use for different portions of the device. And the design rules, again, I have talked about the minimum separation, minimum width. So for every layer or every material, we have a minimum width, minimum length, minimum area, minimum separation, all these defined. So we have specified rules for designing these layouts. Okay, so we'll have to follow these rules, and at the end of creating this physical design or layout, we'll have to verify again that we have followed all the design rules. Okay, so we call that design rule checking, or in short DRC. Okay, so we will have to do that, and if there is any violation of design rules, we'll have to correct that before going to the next step. Okay, so this is another type of verification, you can say. So first we'll talk about the layers that we have. As I mentioned, like let's take the example of NMOS again. So as I mentioned, the first layer is the active area. So active area will tell you where you can place the devices or place your circuits. Okay, so the active area will define, like as I showed that we had a like circular wafer, right? So that will be our active area if you like look at the hardware. So anything inside that circular area, that's your circuit and that you can measure. So similarly, when you make the layout using the simulation tools, we have a canvas. In the simulation, we had a canvas, right? If you will have to place everything on that, like on that canvas. Similarly, in the layout, we will have a canvas. Okay, so the canvas will be the active area here, where we can place our devices, other components like transistors, anything like that. Then we have this polysilicon. So polysilicon is the gate here. So for both NMOS and PMOS, if we want to make the gate, we will have to use this polysilicon layer. So you can just mention this is our gate. Anywhere we have a gate, we need a polysilicon layer. Okay. So then we have this NOL and POL. So NOL and POL is actually makes the substrate. So we know for NMOS, the substrate is P-type, right? So we'll have to use this POL for NMOS. Okay. And for PMOS, we know that the substrate is N-type. Okay. So for that, for PMOS, we'll have to use this NOL substrate. Okay. So if you don't just remember which layer is used for what. If you don't remember, it will be difficult to understand the like physical design, the whole design later. So again, the POL, this OL, NOL and POL are for substrate. So for NMOS, we know that the substrate is P-type, so we'll use POL. And for PMOS, we know that substrate is N-type, right? So we'll use this NOL for PMOS substrate. So this NOL and POL for substrate. And then we have this N plus P plus diffusion. So from the name, you can understand where we'll use that. So can anyone tell me where this N plus P plus diffusion will be used? Like which part of the transistor? Source and drain, exactly. So we know that for NMOS, we have N plus source and drain, right? So for NMOS, we will use this N plus diffusion. And for similarly for PMOS, we'll have this P plus, right? P plus source and drain. So we'll use this P plus diffusion for PMOS source and drain. Okay, so this is for source and drain. And finally, we have the contact. So again, if you remember the breadboard class where you use resistors, capacitors to build some circuit. So we have for resistor, if you had two pins, right? So two pins at the two sides, and which we use to connect with other components, right? So in discrete components, we have pins, but when we make this physical design or like the fabricated chip, we use this contact to make the connections. So for every terminal, so for the transistor, we need to separate this source, gate, drain, and bulb, right? These four terminals, because these will be like when you build the inverter, you know, the gate were connected, the source was connected to something, the drains were connected, right? So you need to make the connections between, like if you make complex circuitry like NAND, NOR, you will have much more complex connection. But you will always make the connection in terms of drain, gate, and source, and the body. Okay, so for these four terminals, you'll have to use this contact so that you can connect them with other terminals later. Okay, so these contacts are for the terminals to make connections. Okay, and finally we have the metal layers. So metal layers are actually the wires, you can say. So if you compare them with the simulation, to make any connection, we used the wires to connect between two contacts, right? You can say like to connect between two drains, we used wires. So similarly here we use the metal layers to make any connection. Okay, and in different tools you might have different number of layers. The tools that we use, we have two different metal layers, M1, metal 1 and metal 2, you can say. And if you use cadence, there you have like six metal layers, you can say. So I'll just briefly tell you what's the reason behind having different metal layers. So for example, if you have a connection, like this is a contact and this is a contact, right? A contact and B contact. If you want to make a connection, you'll have to create a metal, like not metal 1, metal 2, just remember it's a metal layer. Okay, you'll have to create a rectangle of metal to make the connection. Now, if something is there, C contact, if something is there, D contact. Now, if you want to connect this, if you again create a metal layer, if these are the same metal layers, if they over, the metals are conductive, right? So if they overlap, they will be connected together. But if you want to, then you will actually have A, B, C, D, all the contacts connected. But that's not what we wanted, right? We wanted to connect A, B, and C, D, but they will not be connected. So A will be connected to B only, and C will be connected to D only. But if we have the one metal layer and they overlap, they will be connected. That's why if you use this as metal 1, sorry, and if the other is metal 2, even if they overlap, since they are two different metals, they will not be connected. So that's why we have like a number of more number of metal layers. Okay. So otherwise, like if they didn't connect, like if they are not metals, like if they are semiconductors, we could just use one. But since the metals are conductive, they are like, we need to separate them so that even if they overlap, they don't connect with each other. Okay. Okay, so this is you can see the advantage of using tools. Again, we have built-in, like in simulations we had built-in transistors, like we just like drag and drop the PMOS and NMOS in the simulation. Similar thing we can do for layout. So this is the NMOS and this is the PMOS layout. So we have this ready. We will just drag and drop and connect like the simulation. Okay, so this makes our job easy, right? So you see, this is the NMOS, and so here, this is the gate. The red one is the gate. So this is polysilicon, as I mentioned, like for gate, we'll have the polysilicon, and similar, this is our gate. Okay, so this green one is the N plus. So this cross one is actually a contact. I mentioned, like to make any connection, we need to use contact. So this cross is actually a contact. This cross is actually a contact. These two contacts, and these are the N plus diffusion for NMOS, right? In NMOS, the source and drains are N plus. So that's why you see the N plus diffusion here, and this is our actually source, and this is our drain, the two N plus diffusion regions. So you have gate, source, and drain. And similarly for PMOS, this is P plus diffusion. So this is our source contact, and this is our drain contact. And now if you look at the PMOS, so do you remember for PMOS, what was the substrate type? For PMOS, the substrate is N type or P type? N type, right? So for PMOS, you see the green box outside, the dotted green box, this is our NOL. I talked about that, right? So to make the substrate, we'll use the NOL and POL. So for PMOS, we have the NOL. So this is our body. So we have all the terminals, gate, source, drain, and body. But for NMOS, do you have the POL? What is the substrate? Can you see that here? So we have gate, source, drain, but we don't have any NOL or POL, right? But for NMOS, we know that the substrate is P-type. So we should have used an POL, a POL here. But the thing is, like the black area that you see, the canvas is actually P-type. So the big area, the canvas that you will draw on is actually the P-type. So you have the readily available POL, you can say. Okay, so the whole thing that you see here is actually the body. That's why we don't need any other additional POL here. Okay, so this black region is actually the POL. Is it clear? Or is there any question? So this is our NMOS layout. This is our PMOS layout, and we'll use them to like make the inverter first. So again, the next thing is the design rules. As I mentioned, there are many design rules, and the most famous one is the lambda based rules. So what is lambda? So lambda is like the unit, you can say, like for length you have micrometer, meter, anything like that. But for these rules we have lambda. So we will define the width, the separation, all those things in terms of lambda. So maybe width of 2 lambda, something like that. Separation of 3 lambda, something like that. So the question is, what is this lambda? Okay, so when we use or design these CMOS circuits using CMOS technology, you might have heard about like the Apple 5 nanometer chip, right? The MacBook uses the 5 nanometer chip. So, and you all might also have heard about like 7 nanometer CMOS technology, 10 nanometer CMOS technology, or you might not have heard that. So that's okay. So the CMOS technologies are defined like with some number. Okay. So the lowest people could go actually this 5 nanometer, and people are trying to go to 2 nanometer technology currently. So, and Samsung has claimed that they have this 2 nanometer technology, but let's focus on 5 nanometer because that's the commercial product Apple has. So we have 5 nanometer technology. And in the transistor, if you go back, we have this gate length. We have this gate here. So the length of the gate, the minimum gate length we can have in a technology is actually this number. Okay, so if you have CMOS 5 nanometer technology, the gate length of the transistor can go as low as 5 nanometer. You cannot go below that. Okay, so that's how the technology is numbered, like CMOS 5 nanometer, CMOS 180 nanometer maybe. So if you have CMOS 180 nanometer, the gate length, the minimum gate length you can have is 180 nanometer. And the lambda that we have in the design rules is defined by half of this number. So if we have a CMOS 180 nanometer technology, the lambda will be 90 nanometer. Similarly, for CMOS Apple 5 nanometer technology, the lambda will be half of that, 2.5 nanometer. Okay, so lambda is another unit, you can say, like which has a value like this is, you can say this is also, if we defined a unit like of 10 nanometer, so that would not work for any technology. But that way the lambda was defined, it can work with any technology, right? Just the value will change, but the lambda will be there. So if you define the design rules in terms of lambda, that can be applicable to any technology you have, right? So that's the advantage of using lambda in terms of using any number, because with any technology the number will change, but the lambda, the unit will remain same, the value will only change. So these are the rules that we have, like what will be the minimum width, minimum separation, minimum area, and all those things are there. And we don't need to learn this, or we need to remember this, because the tools that we use, like the microwin that we use or cadence that we use, they have these things built in there. So they have a function, like we just click the run, right? Run simulation. So it generated all the outputs. So they have a built-in function called design rule checker. So we'll just click on that and they will check all these design rules for our layout. And they'll tell us if there is any violation or not. Okay, so that's why we don't need to learn all these things. But these are the design rules that we use, and we'll do that. We will check the design rules at the end of our layout. So now let's go to the tool that we use, and we will do that today. So we will use this microwin. I think you have already installed that. And so let me go there. So you are having with, so let's first solve the challenge of registration. You are having that, right? So for that, so we all are here, right? We all are here. So you can, like, one of you can come here, sit beside him, and another. So do you have the microwave installed? Right. There is like Mac. So I told one of you to sit here, not there, and one of you here, because his laptop is not working. So you cannot cover 4 students in one laptop. So that's because they have Mac. There. And you can, if you don't have any, you can give them the laptop. So So first we'll solve the registration issue. To do that, we will go to this help. Okay. In the tool, click on help, click on the register. You will see something like, you will see a pop-up window like this. Okay. Then click on the load license. Again, you will have something like this. Okay. Are you seeing this? Then you have this license file, right? Just click on that and click on open. Yeah, you should see this micro is in trial mode. Yeah, that's it. Then okay, and close everything. So this is the tool that we'll use. And again, you see this black here, the black canvas. This is the canvas where we'll draw our layouts. And as I mentioned, this is the p-type. So this is our p-type substrate, you can say. Okay, and these are the palettes, layers you have. You see, you have metal 1 and metal 2, the two metal layers. You have contact that I explained. We need to make any connection. Then you have the polysilicon, which is the gate, right? The polysilicon is the gate of NMOS and PMOS. Then you have P plus diffusion, N plus diffusion for source and drain. Then we have NOL, which we'll need for PMOS substrate, right? And then we have this text. If you want to write something on the layout, you can use that text. And then on the top, you have this. If you click on this, you'll see this MOS generator. So just compare this with the circuit lab. So there you had NMOS, PMOS transistors, right? Just drag and drop. Similar thing. If you click on this, you'll see that there are two options. One is NMOS and another one is PMOS. So from this, we will generate the NMOS and PMOS layouts. And then there we have complex contacts. We don't need that. Then we have this virtual capacitance. So if you want to connect a capacitance, we need that. But for now, just ignore that. This is a resistance. If you want to use a resistance, you can click on that. This is an inductor. So inductor, capacitor, resistance, you know that. Then we have this ground, right? In the circuit simulation, you use the ground, remember? So we had ground. So you will use this. So this is VDD actually. So this is VDD. We use a voltage source for 5 volt, remember? So that's our VDD. And then this is our ground. And this is the clock. Clock means the voltage generator that you use for the input. You remember the square pulse that you generated? So this is the clock. Here inside the clock, if you click on that, oh, I'm sorry, I'll show that later. So inside this clock option, you have different types of functions that you can generate. You have square, you have like linear function, you have sine wave, all those things. So inside this, you have all those things. So we'll use that for the input, and this I sign is the output. Okay, so for the drain, like in the inverter, we connected the two drain, that was our output, right? So this I will go there, and I will determine which like node we are more interested in, like which is our output. So these are all the things we'll use. Okay, so again, and there are other options as well. I'll briefly explain. So this is our this is rectangle draw box. So if you want to draw any, like maybe metal 1 rectangle, just so how to draw it, I'll explain. So just click on this rectangle box, click on the metal 1 layer, because we want a metal 1, for example. Then click on 1 and press, and just like you can say drag, you can click and drag. Okay, click and don't maybe release, click, press and draw. You see, so you can choose the dimension. Did you get that? Like click, don't release, click and keep pressing, and then just drag to define the dimension. Then if you release, it will create a rectangle of metal 1. Okay, yeah, just we'll not use this, just to show how to draw a rectangle. And you can use like polysilicon maybe, and you can do the same thing here. You can create a polysilicon layer. So we'll not use this, we just wanted to show. And this gun sign is the delayed option actually. So if you click the gun, and then if you similar thing, click, press and drag and mark all these things, it will delete. Okay, so these are the options we have, and then we'll use this one mostly. So this is the move and stretch. So for example, again, let me draw a metal 1 layer. Now if you want to maybe make this longer, okay, in the x-axis, so you will click on this stretch option. You see, very small, I'm not sure if this is visible. Okay, move and stretch, this option, click on this. And if you want to maybe enlarge in the left side, then you can just click on the left side. And if you just like click and then just move the mouse or move the pointer, then you will see that it will allow you to stretch. So you can just click again, it will stretched, it will be stretched. Okay, and then you can also move like similar option. Just first you'll have to mark this, and then you see you can just take it anywhere, and if you click it here, it will be moved here. Okay, so these are the move and stretch options. So these are the options we will use. So that's why I first gave you an idea about that. Let's delete these things. Okay, so did you all like, were you all able to do the move, stretch, all those things? Because move and stretch, these and rectangle drawing, these three we'll use mostly. So draw a rectangle, move and stretch, these three. Could you do that? However, like everyone, like I'm just making sure if you could do that, then we can go to the next step. Okay. So next step is to like we'll draw the layout of an inverter. So I'll draw the circuit here. That will be useful for you just to understand. So this is our PMOS. This is our NMOS. The gates are connected. This is our input VU. This is our output. This was connected to a voltage source which was VDD. Let's call that VDD. And then here we had our ground. Right. So this is our circuit that we want to create layout for. So first we'll have to create a PMOS, right, on the top that you have. So for PMOS, click on this MOS generator. Can you, I'm not sure if that's visible. So here, click on this MOS generator, click, and then click on this in lambda. I talked about the lambda design rules, right? So click in lambda and make it maybe 5. Because if you make it too large, that will be like, that will take a lot of space. So let's do it like 5 and length 2, similar thing, and click on the PMOS because we want to generate the PMOS first. Okay, PMOS, then generate device. You'll see something like this, and then you can click where you want to. No, I'll explain that. For inverter, we don't need that. Yes, just click on somewhere on the top mostly because the PMOS will be on the top, right? So put it on the top. Sorry. That's because of the one that I thought, did you change the size?
What is the
I think that's because of one level. I think my case it's not one level. You can just do with the just most generator. Yeah, I will show you. Yes, please. Oh, it will depend on the skill that you have. Oh, but if you put the same number that we did earlier, like I'll show that again. So let me delete this. So go to this MOS generator. This, you see the first one. I'm not sure if this is visible. MOS generator, click on that. You'll see something like this. Then click on the in lambda option, units here. Here, click on the in lambda option, and then put 5 as the width, and then click on the PMOS here, and here PMOS, then generate device. So you'll see, then you can put it somewhere here. I showed you the resistance, the registration. So you do that. Like whoever is having this issue. Was having the issue. Well, I showed you the registration process. You know that?
No.
Now you can do the same thing. Where is he? Where did he go?
Oh, he went to the bathroom.
Okay. Yeah, okay. So I think we have all of us have been able to bring this PMOS, right? Yeah. So now next step is to bring the NMOS. The same thing, go to this MOS generator. We will use the same size. Just click on the NMOS and generate device.
The 5 and big thing.
Yeah. Let's keep them safe. So then put it here. Something like this. So you have this PMOS and NMOS. Okay. Then you see you have a all option here. So view all. If you click that, it will give you some optimized view where you can have similar view like this. Okay. Yeah, PMOS and NMOS are there, right? So have are any of you having any issues to do that? Or any questions? I'll go to the next step if it's okay. Okay, so after we place this PMOS and NMOS, and we know that there must be a minimum separation between the PMOS and NMOS, right? So I'm not sure because we don't know, we didn't read the design rules, right? So we don't know that. So what we can do, we can actually do you see this button here, design rule checker. Look at the slides, everyone, after putting the PMOS and NMOS. If you miss one step, that will affect the next step, So every step is important. So if you this is the design rule checker that this tool has. I talked about this, right? So these will check the design rules if we are violating any rules or not. So if we click on this, it will show what it should not happen. So are you having, so just click on the design rule checker. Are you seeing this type of things or not? So forget about my screen. Just do yours. You're doing the same thing. So this is again like an error of the tool. So the transistor we use from them, right? So there should not be any error. And the thing is it sometimes shows errors, sometimes doesn't. So that's the weird thing. So is there anyone who is not seeing this type of errors? You are not seeing. So yeah, here. The green one. Same thing, right? Not sure why is it doing that. So let's delete everything. Yes. Or maybe close the tool. Because I've seen that this worked earlier. I'm not sure. Because the transistor that we imported, that's from their library. That should not have any errors, So go to microwind. So let's just restart the tool and let's see if there is any error. Yeah, just like use the same length and width that they have. So like the transistor itself should not have any error, because it's their library. So and here you can see that there is no error now. So I think yeah, keep 10. Keep 10 as well. Yeah, the same width 10. Yeah, in lambda, keep the width 10, length 2, and just import the PMOS. Okay, and the same thing, do the NMOS, same width and length. Just click on the NMOS and put it on the bottom. And then click on view all. And then again, do the design rule checker. And yeah, you see there's no error now. So now if you check that, like click on the design rule checker, you'll see that there is no error now. Okay, you see in the left, here in the left bottom node, I'm not sure if you are seeing this. You see no design rule errors. Congratulations, something like that. Okay, so up to this point, there is no errors. Then we'll go to the next step. So again, the steps are same like the simulation. If you remember, after dragging and dropping the PMOS and NMOS, what did you do? Making the connections, right? We connected the drains, we connected the gates, all those things. So let's first do the gates. So the gates here, we have the same material. So I'll have to, so try to align them first, because otherwise you'll have a zigzag connection. So just use the move option if it's not aligned. So yeah, oh, it's not aligned now yet. Yeah, so just try to align this polysilicon. You see there are the dotted line. These will be the pointers for you to align. So try to align these two polysilicons like vertically. Okay, if it's already aligned, that's fine. If not, then you can use this move option, move, and then select on the NMOS, and then try to align the polysilicons, like the two red vertical lines you see. Like again, another way to examine if they are aligned or not, just click on the move stretch option, same option, and try to stretch this polysilicon and see if they align perfectly, right? And if they are aligned perfectly, you can just make this connection by stretching. Okay, if they are not aligned, then you can do that. Actually, then you cannot use this stretch option. You'll have to create this rectangle. You have to create these boxes. So that's more difficult. But if you just align them perfectly, then you can just stretch one polysilicon and make it connected with another. Okay, and if you think that like alignment, like making them aligned is difficult, then you can just use this polysilicon and create this draw boxes option, and you can do something like this. You can create a polysilicon like this, and then if your NMOS polysilicon is here, you can create something like this. This way you can also make the connection. You just have to connect the two polysilicons. Okay, I'll show that. Just let me delete this. Let me delete this extra. So you have this move stretch option. You can see here. Is it visible? Click on this, and then just click on any of the edges, the edge that you want to stretch. Maybe for PMOS, you want to stretch the bottom, edge. For NMOS, you want to stretch the top edge. So just click on that and then just move the pointer. Are you able to do that? Yeah. Yeah. So the gates are connected, right? So are you able to connect the gates? Yeah, now next thing is like we'll have to connect the drains, right? The drains will be connected and that will be our output. So drain will have to, again, since we have aligned these two transistors, so we'll be able to just stretch, same thing, stretch the metal layer. So we want to stage this one. Just click on the bottom edge and move the pointers and just make them overlapped. Okay.
Both sides.
No, not source. Source are not connected, right? So we are making these connections. So we have first connected this to gate to the red wires, the polysilicon, and then we have made this connection here. The drain. So this is done. This is done. Okay. So now we are left with like these connections. The source of PMOS will be connected to VDD, and the source of NMOS will be connected to ground. Right. So we'll have to make these two connections now. Sorry. So I think like the gate and the drains are connected, right? Is there any questions up to this point? No. So have you been able to do that? Gate and drain connection? Yeah, okay. So now next connection is like, if you look at this, we have done this and this. Now we'll do like the source connections are only remaining, right? The source of the PMOS will be connected to VDD and the source of the NMOS will be connected to ground. So let's first from here, you see, this is our VDD. You see the VDD supply. So we'll select that and connect to the source VDD. Just click on there. And source of the NMOS will be connected to ground. So this is our ground. Just select this and click on the source on the NMOS. See? The source of the PMOS is connected to VDD and source of the NMOS is connected to ground. And again, in the beginning of today's class, I mentioned about like the source and body, right? Source and body are connected together in most of the cases. So in NMOS, we need to do anything because we are using the canvas as the body, right? But for PMOS, we have an additional layer, which is the annual, the green one. And that should also be connected to where? The VDD? Yeah, so okay. If I delete, I think it will delete the layer. So I'll just show it from here. So this, you can see this is the VDD supply. Just select it and click on the source of the PMOS here, anywhere. Are you able to do that? Just select on the VDD supply. And yeah, so it's done. No, okay, similarly, connect the ground. So the thing that you have here, this is one, this is your ground, right? So just select this and connect it to the source of the NMOS. So here, this is a ground. See the ground. So you can look at here, the source of the NMOS is connected to ground, right? Here. So we are connecting a ground to the source of the NMOS. So is this done, the VDD and ground connections? Okay, the next thing is you'll have to, okay. Yeah, I was talking about the body, right? So NMOS does not have any additional body because we are using the canvas as the substrate for NMOS. But for PMOS, we have this green annual region, which is the body of PMOS. And we mentioned that the body is typically connected to the source terminal, right? For the NMOS and PMOS both. So since the source is connected to VDD, the body should also be connected to VDD. And since they're separate, we'll have to manually do that. So we'll have to again create, like click on the VDD supply and we'll have to place that on the body or the annual. to connect the body of the PMOS to VDD as well. Okay, so the VDD ground connections are done. We are only, so the only thing is remaining is the input connection and the output connection. Again, if you remember the simulation, in the input, we connected a voltage pulse, right? Signal generator. So as I mentioned, the clock here, the one beside the ground. So do you have any question to this? Sure.
In the big open space.
The green space.
Yeah, the outline space. I can't get mine to go there. Like,
Are you trying to put them on the black surface or on the green?
ignore this.
So this should be GSS.
That should be yes.
So the ground of it is NMOS, right? The ground of the NMOS should be good. And the source of the NMOS should be ground.
Okay.
Source of the PMOS should be VDD.
So then
Then you should have another.
then it will have trouble there. Oh, okay, that's why, because it was recognizing that there.
Yes.
Okay.
Everything was VDD.
Makes sense now.
Okay, so now we'll have to connect the input. Okay, that's the only thing remaining. So for input, we used a square pulse. You remember, like 0, 1, 0, 1, right? So we use the same type, like we use this clock here. You see, the one beside the ground clock. We'll click this and place it on the polysilicon or gate, which is our input. So we'll name this as input, and I will keep it as it is. So we have this like time here, like how much it will be high, how much it will be low. So we have 0 and 5 voltage. That's what we want. So we'll just assign. Okay, so this is our input. And the final thing is remaining is output. We'll have to declare which is our output. And for that, we'll use this I sign. So click on the I sign, and this is our output, right? The drains. So we'll put it anywhere here, and we'll just name them as out. So this is the complete connection, right? There is nothing left, or are we missing something? Do you have any question about anything? So we have done all those things, right? The input, output, all the connections, and again, finally, we'll again check the DRC rule from this design rule checker, and it should show no design rule error. Okay, and then we'll just run the simulation here. So you see the green play button here. Just click on that, run simulation. You should see something like that. One, you can ignore one. So I think you have other solution. You get the output, but I think the error is from the other circuit. Yeah, I think that's still there. Yeah, see. If you select this all of so yeah, you see this green one. Yeah, that's the answer. Now, if you run the yeah, yeah. The green one is the input and red one is the output. And if you compare this with the simulation results that we had, does this match?
Yeah.
Click on the eye. Place on place. Name it out. You do the info. Click on the on. Then the gate,
Yeah.
the gate should be right. So you have to use one block.
Gravity.
And we did the same. Oh, just the same. Then check the example. So, what is that? So you place it very close to the very nice to move to the atmosphere. More.
No, just a stretch those down to the others.
That's 6:33.
This time, when you stretch the polysilicon,
Mm.
the other one was also stretched. You see the gate of this atmosphere actually.
I think, yeah, I think that happened when I was trying to move it
Yes.
or something, because the
Yeah,
gate.
that- And then turn it down. Try to do it as much as separation between them. So did you get this type of output? Yeah, and you can make sense of that, right? For logic 0 again, you should get logic 1 output, and for logic 1, you should get logic 0. So you can now use it. Even you have gone to the full circuit, right? If you have any question at any point, you can ask me. Just try to do it on your. You didn't put the output. Oh, this is not. So these two should not be nice. So this source is connected to BD. This source is connected, should be connected to ground, not BD. Ground source of NMOS. And this should be your out. The drain is your out, right? So this should be your and then this should be your input. Yes. What I.
Yes. This is how, right?
Yes.
The clock is the gate. So that's, so the ground. So wait, this. And. The out is off. So what about the labels? And it's, I just labeled orange. I think. But we're gonna have to do that too. Simulation. Tomato process. Like, you just get nothing with this. I'll look it up then. What?
Sure.
I saw that in this little guy.
Yeah. Yeah.
I have one question.
Yeah.
So I'm missing the VSS and I don't remember typing the VSS. Again, it's- Let's see. Okay, this time. Is it okay then? It says it out.
Yeah. Yeah, I think the input is different. But this is what you see. The input is 0 of this one. Input is 1 of this. Working, but input needs to be different. Yeah, you see the times. Make 0. The surface button. What button? The ring process. long time. So how many of you have been able to do that, like to get up to this point? Yours is not working? Should be like to be able to do kind of community. Sure. You could die. No. You minimize that. So this is not this. Like, do you minimize that or close that? Or
Simulation.
it's the passage. I think the input was used long. Yeah, I
Thank you.
okay. So that's it. Thanks so much. It's like you just have a account. You have an order. You have a card. Sure. Yeah, we can skip it because I think I'll be done in like more than 30 minutes, 30 more minutes. So yeah. So I think everyone has done the inverter, right? So yeah, if you again go to the, if I go to the slide again, you see we have done actually the whole step before like up to the fabrication, right? We have done the like design, logic verification, physical design, physical verification, right? So the output that we got at the end after the physical design, there was the physical verification, right? We use the layout to do the simulation. The final step is to now to send this physical design that we made to the foundry for fabrication, and then when you get the chip back, then we'll again have to do the verification there. So the next thing we want to do is like this is a pretty simple circuit. So we want to do a more complex circuit, like layout for a more complex circuit. So we'll do NAND. Okay. So we'll not do the simulation because we have done that earlier, I think, right? You have done the NAND simulation with the circuit lab. So I have that screenshot here. So we should have something like these results, right? So NAND, you know, for only one input case, we get 0. And for all the other 0, 0, 0, 1 or 1, 0, we get 1 as the output. And that's what you see here. For 1, 1, we are getting 0. For 0, 1, 1, 0, and 0, 0, we are getting logic 1 as the output. Okay, so this should be the output for the NAND circuit, and we want to, so this will be here. So now you will do that actually. So I will not show you the physical design anymore. So I think I'll just remind you the steps. The first thing is you'll have to bring here, you'll have to bring two PMOS, right? In NAND, we have two PMOS connected in parallel and two NMOS connected in series. So you'll have to bring two PMOS layout from the MOS generator. You'll have to bring two NMOS from the MOS generator. And then you'll have to place them side by side. And then you'll have to connect them, right? Like the way we did. Like here you see the gate of one PMOS and one NMOS connected together, the gate of other PMOS and other NMOS connected together. So we'll have to do that. And then we'll have to connect the drain and source of the two PMOSs connected together. And then that would connect it to the drain of the one NMOS, and similar thing. Like you'll have to do these connections actually one by one. And finally, we'll have to connect these two input, and then you'll have that VDD ground connections eventually. And finally, you will do the verification. Okay, so start doing it, and if you have any questions at any point, I will just let me know. Okay, so the goal is to design the layout for this NAND circuit, the two PMOS and two NMOS circuit that we have. Sorry. Yes, in the micro, yeah, layout. Oh yeah, top that's so start doing like just first bring the two PMOS. Getting rich. Yeah, so yeah, everyone is having the same issue. So if you don't see this palette, if you don't see the palette, you can see mine is also gone. So if you don't see the palette, like the layers, you can just click on this one here, show palette. Yeah, if you click on the show palette, then this will appear. Yeah. Oh, sorry. So bring two PMOS, same 10 width, same side, two PMOS, two NMOS.
So I can be most on the top.
Yes, yes, obviously the pull up, like on the top, we'll always have PMOS. And try to keep like this. So this is one PMOS, this is one PMOS. Put them side by side. Remember the gate, like one PMOS is gate. So this is our gate, right? This will be connected to the gate of one NMOS. So you should put one PMOS here, one NMOS here, like this. And similar thing here, one PMOS, one NMOS, so that you can just connect the gate. Yeah. Then you'll have to, but that will make your like source and drain connections difficult. But you can do that later. Just try to align one PMOS, one NMOS, like the inverter, one PMOS, one NMOS. So like the two sets of inverter. Yeah, you don't need policy, right? Yeah, but yeah, that's the other one. And if you need to like zoom in, zoom out, you can do that. Yes, yes, yeah, and two. Try to keep some separation between the two PMOS because like, and you can also check like after putting two PMOS, if you have maintained the separation, minimum separation, you can just click on the design rule checker. Like after every step, you can check the design rule. Then will like say like you can just yeah you have I think overlap, so there will be an error. You can just move. Yeah, you can click on the design rule checker to see if there is. So you have to like take that further. Yeah, we are not optimizing the area of the layout, so you can just like keep as much as separation you want. You like so NMOS this should also be there. So this gate will be connected. Okay, okay, yeah, but I showed it here. You know, like gate of one PMOS will connect to one another. The other will be that same. So
This one
this gate will connect here. This gate will connect here. So you can't do that. Like, you can do that, but like, there will be different direction. I think we have selected the wrong one.
And then the same thing in line with the PMOS, right?
Yes, yes, yes,
Then activate it.
yes. Like, you can now check the design will check, right? Yeah, you see there is an error. Metals, you have an addition of metals, so when you move, yeah, now.
I was just gonna.
Now make the gate connection first. You see, one PMOS gate, one NMOS gate connected, one PMOS gate, one NMOS gate connected, and these will be your two inputs. Input one, input two. You'll have to connect. Look at this connection, right? And you have to connect the gate, right? This gate will be connected to this one. One PMOS and one is connected. So look at the circuit. So the gate of one PMOS is connected to the gate of one NMOS, right?
So these two printers will,
Yes, yes. Exactly. Yeah, like that data, right? So, but is that you see if you check the design rule, there will be an error because there is no separation. So minimum separation, so you have to move this as well. Then you have to align this with this one, and this one with that. Is this visible to everyone? The circuit?
Kinda.
Because I was also trying to like take the micro wind in the screen so that I can also do that. Because that will take away the. Okay, I'm not sure how we can do that. Can we? Yeah. Sure. Yeah. So as I mentioned, we need to bring two PMOS, right? So first bring one PMOS here on the top and another PMOS on the top. Try to keep as much as separation as you can. And if you want to check, you can just do the design rule checker after every step so that you see like there is no design error. And then you need to bring two NMOS, right? Now try to align the polysilicon here and as well as okay. So the devices are here. Then we'll have to make the connection. The process is same. The steps are same. So we'll have to make the connection. So let's first talk about the gate connection, right? So you see one PMOS gate should be connected to another NMOS gate. Okay, so let's trace the polysilicon and connect this similarly to this to this. So if you look at here, we have done these two connections, like this gate of PMOS, this gate of NMOS. These are connected. So this is input one. Similarly, this gate of PMOS and this gate of NMOS connected together. So this is the input. So we have done these two connections. Okay. So now for PMOS, you see the source are connected together, both the sources, and both the drains are connected for PMOS. So if you and also if you like you see this is the source, right? This one is source, this one is source, and this one is the gate, this one is the gate. Oh, sorry. So this one is source and this one is drain, right? These two are like the source should be connected together and the drain should be connected together. So let's do that. And since they are not aligned, we cannot stress now. So what we'll have to do, we'll have to use now rectangle that I showed out in the very beginning. So we'll use metal one. Let's click, press, and drag. So let's create something like this and then something like this. Metal and polysilicon can overlap because they are two different layers. They will not be connected. We'll have to just make sure that two same metal layers are not overlapped when we don't want them to connect. Okay, so these two like drains are connected. Similarly, we have to make the source connected. Now we cannot do the same thing here because these will be overlapped, right? We want to connect this one to this one. Now if we want to connect this to the like this way, so there these two metal layers will be connected. So we'll have to do that from the top. You see, after this, let's check the design rule checker, and you see no design rule detected. So what we have done, the sources of PMOS are connected, the drains of PMOS are connected. That means these connections is done, and this connection is done. Okay, so I will wait for you, like just first do this up to this point. Connect the two gates. I think you have already done that. Then connect the sources, source of PMOS and drains of NMOS. Have you done that, like up to this point? So if you have any questions, please ask me now. Otherwise, like after doing all the things, if you ask something like here, we'll have to redo, right? So let's go step by step. No, same thing. The metal one layers. So I think we'll not need metal two here because this is not that complex. So we'll be able to use only one metal there. Just try to understand the process so that you can do that on your own later, right? So we'll give you some homework as well to make layout. So try to understand the process, like the way I am doing, like take one connection from the circuit and try to implement that in the layout. So do that step by step. Are you done? How many of you have done? You can undo. I can click on edit and undo. You can also save if you want, like after doing some steps, you can save it as a file. Then like in that way, you'll be able to like bring that later if you delete. We done the conditions. You check it. Yeah, I actually also like missed one thing. Like you can also do that. Like instead of like if you remember, I created a rectangle here and then the long one. You can actually stress that as well. The source here. You can stress that up to this point. Then you'll just need only this long rectangle, then you can trace it here again. Right? Yeah. Can we go to the next step, or is anyone?
Yeah. I have one, but it's.
Oh, well. It has two elements. So what you can do is delete the PMOS section between ones. Just click on the all. These might use try to put the PMOS aligned. So only this and when you put the PMOS right aligned. You can use the dotted line.
Okay, so
So how many of you are able to do up to this point? You can raise your hand. Yeah. So he's, yeah. We'll wait for him, then we'll go to the next.
the people who doesn't have a Windows, what do they from you? Like, you can download either. What is it? Like 4 people.
Yeah, I thought, like, you could share that as well, like, you can do the next part. Just
After
have
that,
to,
but
after that, I'm not sure. What can I do?
you have extra laptops there.
I'll have to talk to Dr. Aziz about that, I'm not sure. But do you have any Windows computer even in your home, like in your desktop? Yeah, then you can use that. Yeah, you can just, you can use the same tool. Yeah.
How about did you?
Nothing. Well, just-
They have all the. She can try the desktop, right?
Yeah, yeah, you can use that. Like, you can see the videos, like, and then you can try that. Yeah.
Who's uploading the videos?
Dr. Aziz should do that, I'm not sure.
It's not up to me.
Yeah.
Not the homework.
Sorry,
How will we submit the flyer for this?
you just like do this layout in the tool. You take the screenshot. And you also take the screenshot with that, where you see that. Here, you also submit out.
We have not covered the whole market.
No. So are you have you do that? Yeah. Okay, so we'll go to the next step. So everyone, so just again, like try to understand the process, how we are doing this, right? Because you will not, like in the homework, you will not do the inverter or NAND. You will do another different circuit.
Oh.
So the process will be the same. You'll have to go step by step, right? So the first step was like bring the transistor, like 2 PMOS to everyone here. So the first step was to bring the PMOS and NMOS, right? And the second step was to make the connections. Like we went one by one. Like we first make this connection, like gate and gate. Then we did this one, gate and gate. Then we did this one, drain and drain, source and source, right? So next, what are remaining? Like we have to make this connection, we have to make this connection, then we have to get this ground, then we have to get the VDD, the inputs and the out. Like this is the whole step. So just remember this, because when you do the other circuit, you'll have to go through the same steps, right? So like again, let me use this manner. So we have done this, like the gate connection, the source and source, PMOS, drain and drain PMOS. Now let's do this one. So what is this one? Like the drain of, now this is the same thing, right? Both the drain of PMOS is one node now. So this is like drain of PMOS, and this one is drain of NMOS. Which NMOS? Which the NMOS that is connected to the first PMOS. Okay, so if you look at your layout now, so this is the drains of PMOS, right? This blue layer here. Look at the slide screen. Look at the projector here. So if you have this is the drain of PMOS, right? And you need to connect that to the drain of NMOS, the NMOS that is connected to the first PMOS. So this is our first PMOS. Let's assume that this is our first input one. So this is our first PMOS, this is our first NMOS. So this drain of PMOS will connect to the drain of this NMOS. Okay? Like, is there any question about that? Again, look at this one. So this is the drain of PMOS. This will connect with the drain of NMOS, the NMOS that is connected to input one. Okay, so we are assuming that this is our input one. The first, this red one is input one. So this is our first NMOS. Okay, so the drain of this NMOS will go to this drain of the PMOS. So if you want to do that, you can just stretch, right? So you'll just have to stretch this drain and connect with this one, right? So this connection is done. Look, right? The drain of NMOS is connected to the drain of PMOS, right? So this is that connection. Now the next connection that we have is this one, which is like the source of this NMOS is connected to the drain of the other NMOS, right? So this is the source of that NMOS here, and we'll have to connect this with the drain of the other NMOS, which is this one. So we'll have to go from here to here. So we can again first do the stretching here, and we can stretch it here as well. And then we can just create a metal one layer. Like this. Right? So this is this connection, the source of that NMOS and the drain of this other NMOS. This is source, this is drain. They should be connected. So now if we run the design rule checker again, You see, no design rules detected. So up to this point, this is, we are good actually. We don't have any error. Have you done up to this point? Just let me know. Is it done? Have you done that? Did you check the design? So we have also done this now. So this is done, this is done. So all the connections are actually done. If you look at the circuit now, the only thing is remaining again, this VDD connection here, this one, this ground connection here, this two input connection, and this output connection. So these 5 things are remaining. Okay. So let's first do the VDD. If you are done up to this point. So are we all done? What happened?
But it's fixed.
Okay. So are you here? Are all of you here? So can we go to the next step? Yeah. So okay. So the next step is to connect the VDD and the ground. So like that, if you look at this, the VDD should be connected to the where? Where should we connect the VDD? Where should we connect the VDD? This is the source of PMOS, right? The source of PMOS. So and this blue, this large blue layer is our source of PMOSes, right? These are connected. So the VDD from here, we will bring the VDD and we will connect it here. Simple. And then we will connect the source. Ground. Ground is connected to the source of the second NMOS. You see there in the NMOS, there is only one terminal unconnected, right? So this is not connected to anything else. So this is the other source. So ground should be here, right? So now this connection is done, ground, this connection is done, VDD. Now we will connect the input and output, but we will have to connect VDD as well to the body of PMOS, right? Remember that? The annual of PMOS, they should also be connected to VDD. So we'll have to bring VDD to connect here, another VDD to the two annual that we have. Okay, then we have all the VDD and ground connections. Now we only have to do the input and output, right? So output is simple. So we just have to bring the I, but where should we put that? The output should connect at this drain and this drain connection, right? So I think this one here, this one is our output. So have we done the VDD ground connections? Like the VDD to the source of PMOS, the ground to the source of the NMOS, right? So this is our this is our ground actually. This is our ground, and the VDD is on the top. And then we will also have to connect VDD to the two annuals that we have, like the green layers. We'll also have to connect VDD, right? We have done that. Then we also have to connect the output. So I have also done the output. So output is this point, right? Where the drains are connected. So this is our output. You can see here. So we are only left with the inputs now. So these two red ones are the two inputs. You know that, right? So we'll bring the clock again, same thing. We'll bring one clock here, which will be our input one. So we'll have to now change these values because for NAND, if we use the same two inputs, some like this, like input one, input two. The problem is if you have this, you will only have like 0, 0, 1, 1, 0, 0, 1, 1, right? Because this is one input one, this is our input two, right? So we can only have 0, 0 and 1, 1 combinations. We don't have the 0, 1, 1, 0, those other two combinations, right? So we'll have to change this. So we'll use 1 as 0 point, like maybe 1. So for the first input, we'll use 1 nanosecond for low time and 1 nanosecond for high time. Okay. Because if we make something like this is 1, right? This is 1 nanosecond, 1 nanosecond. And for the second one, if we make this 2 nanosecond, like 2 nanosecond low and 2 nanosecond high, you see we have 0, 0, 1, 0, 0, 1, 1, 1, all the 4 combinations, right? So that's what we will do. For the first one, we will use 1 nanosecond for low time and 1 nanosecond for high time, and we'll assign. And for the second input, we will again bring a clock, and we will do that like 2 nanosecond for the low time, 2 nanosecond for high time, and we name that as input 2. Have we connected the inputs? For input 1, we will use 1 nanosecond for time low and time high. All the other rise time, fall time will remain as it is. For the second input, we will use 2 nanosecond for time low and time high. That rise time, fall time will remain the same. Okay. Now we'll check the design rules again, and then we'll just run the simulation. Okay, that's the output we are getting, and you should be able to verify that, right? We remember for NAND we had 0, 0, 1 output, 0, 1, 1 output, 1, 0, 1 output, 1, 1, 0 output, right? So you can see that the first one is 0, 0. We have 1 output, then 1, 0, 1 output, 0, 1, 1 output, 1, 1, 0 output. So only for 1, 1 cases we have 0 output, and for all the other cases 0, 0, 0, 1, 1, 0 we have 1 output, right? That means the layout that we have designed is working properly. Have you got the same output? How many of you got the same output? Yes, I see 2 hands. You can just check, like for 1, case you should have it, right? Yeah, this is 1, 0. Between 1, 1, 0. For other cases, like 0, 0, 1. Oh, that's because of the rise time fault. When you design, yeah, if you make that 0, then it will be like the idea. But in same thing. Same thing. Oh, those are like yours one is much better actually. Like those one is like the noise you can see. So ideally it should be like check, but these are like noises. That there might be different reasons. That's what you see in the physical design. You didn't see that in the simulation. You see that like they were ideal, but these are more practical. And when you have the chips back, when you research them, you will be like more practical. There will be more noise. Carry. Maybe 5. Yeah, now you see like for 0, 0 you have 1, 1, 0 you have 1, 0, 1 you have 1, 1, 1 you have 0. And you can now if you change the time to 10 nanosecond, it should look like this. You got the same result. Just care about the output. Yeah. Yeah, so I think most of us have been able to do that. So have you like the question is like have you got the process like the steps to design a layout? How like these will be your input, right? So from the like logic design and the logic verification, you will have something like this, a circuit, like with PMOS and NMOS. Then with this, you will have to create the layout. Okay, so I've tried to like tell you the steps, right? So these steps will remain the same. So whatever circuits you have, whatever circuits you try to create physical design for, so the steps will remain the same, right? You will have bring the PMOS, NMOS, then you'll have to make the connections, all the drain source gate connections, and then you have to connect the VDD ground and then input output and two additional things which are like annual connection, right? These are not here. So for PMOS, how many? If you have 3 PMOS, you have 3 annuals. So you have to connect VDD to those 3 annuals. Each of the annuals should be connected to VDD. So that's only thing that is not here in the circuit. But you have to remember that. And then if you'll have to connect the input, output, and then you just have to run the simulation and then do the verification. That's it, right? So so I think I'll post the like the homework by today in the so I will give 2 circuits to you. So the one will be like the NOR, the same like similar thing where you will only have the opposite thing like the PMOS will be connected in series now, and the NMOS will be connected in parallel. Yeah, so the opposite like they have PMOS are parallel, NMOS are series. So in NOR the PMOS will be in series, NMOS will be parallel. The same thing, right? So you'll have the same input. So you use the same type of timing for the inputs, and output should be like for NOR, you should have only for 0, 0 cases you should have 1, and for 0, 1, 1, 0, 1, 1 you should have 0. That should be the output for NOR. So and that you will have to verify. So and in the report for the homework you'll have to first like maybe you can draw on your hand and you can like add an image, or you can even use circuit lab to create this circuit. So you'll have to add a like snapshot of this circuit, the NOR circuit. Then if you do this like for that you don't need to do the simulation because you know the output, right? So we just have this snapshot of the circuit, then screenshot of the layout, the final layout that you will be designing. So let me go here. Locked. Yeah, you'll have something like this, right? A layout. So you'll attach the screenshot of that, and also you will do the design rule checker at the end, which will show. So when you take the screenshot, take the screenshot of the full screen so that we can see the layout and as well as the DRC result, right? So these will be there, layout, and at the end you will have this type of result, simulation result from the layout, right? A screenshot of this screen as well. Okay.
Okay, so he wants to drop this off first, circuit lab with the other diagram.
That's optional. That's optional. You can even draw it on your hand and you can add an image of that. But if you want to do that, you can do that in circuit level.
This is what we need to screenshot, the layout and then
This
the
result,
simulation
exactly.
and then the DRC.
DRC is optional because if you have any errors in DRC, you will not be able to do the simulation, right? So if you have the simulation results and that's working properly, that means the layout is correct and there is no DRC.
Would you have the variables, like you were going over with the zero, where they're like what we're supposed to input and then maybe.
Yeah, for NOT gate, you will have the same timing, right? 1 nanosecond for the first input, 2 nanosecond for the second input.
Oh, okay.
Same. The idea is we'll have to get all the combinations like 0, 0, 1, 0, 0, 1, 1, 1. If we like, as long as we get that, that's fine. So that will be NOR, and I will also add another circuit. And I think Mazhar showed you how to like convert any logic function. Right? If you have something like this, AB plus BC, A is equal AB plus BC. So he showed you how to convert this circuit in this NMOS PMOS circuit, right? You remember that? So that might be difficult, but I think what we can do, like the idea of this homework is not to understand this one. So we understand, we want you to be able to create the layout from a circuit. So I think I will attach a circuit instead of this, like maybe a complex circuit, 3 input maybe. And for that, you will have to do the whole process. So the first thing will be the NOT. I explained that, right? And the second homework will be another circuit. I will give you the circuit like this, drawing circuit. And for that, you'll have to first implement that in the circuit lab, do the simulation there, and then do the layout, and again do the simulation. So the whole process. Okay. So these two will be your homework. And like again, I'm sorry about like I cannot do anything, right? The tool is not available for like any other operating system like except Windows. So that's their limitation, I guess. And again, like we don't use these tools, as Nolan mentioned, we use Cadence. So that's the industry standard tool for creating layout. And again, like the technology that we're using here is like 1.2 micrometer. No one use that anymore. So we are now using some nanometer scale technologies. So we cannot do that in this program because, as I mentioned, to have the access to Cadence, you will need UTK ID, UTK email, and then you can get that. But I think that will. I'm not sure if like I'm not sure they are still trying that. I'm not sure. So if they can do that, then I can. Or in the worst case, what we can do is we can we have access. Like we can bring our laptop and we can at least show you like what are the new things there, right? So the process will remain same. So you will again drag and drop the NMOS, PMOS and make the connections with metal layers and all those things. Yeah, I'm not sure about that, but the last time I talked, you don't have access to that yet. So that's why we decided to use this free tool. Yeah, but what you can do is if you can have the access, that's the best case scenario. So we can actually go to our lab on even you can access the tool from remotely as well. Like we can log into the server and we can use that. So that will be the best case scenario. But if we don't have that, then what we can do, we can like use our own ID and we can show you at least like what are the differences there. But as I mentioned, the process will remain same. Just there you will have like more advanced CMOS technology. But and also like the transistor that you are seeing here, source, gate, drain, red, green, all those will remain similar, like same thing. Okay, so NOL, POL, all those things are similar. So I think, yeah, for today we are done.
Posted on Google.
Yeah, I'll post that on Google. Yeah.
I'll look those there. And also this lecture.